Hey ladies and gents, we're taking a look at a lab video that will be useful for Unit C on correlation as well as Unit S on simple linear regression. So I've got a template made up called the Correlation and SLR template, and you can find that in the supplementary files folder of the Blackboard course. Let's take a look at what we're dealing with here. I'm dealing with the Business Admin 111 survey data. This is the data which I used in my data cleaning lab videos. And so these data have been cleaned up here. And what I've done is I've actually made copies of this particular page right here. So you'll find them over here and here and here, because I want to run through some different examples. And what I usually do is I always go back to the first page here, which is called clean data or original data or whatever, and I highlight everything and then change it red so that it tells me, hey, don't mess with this data. You can make copies of this, but don't mess with the page that has the red data, because that's the original data. So anyways, I've made a copy here, and I'm going to take a look here at the relationship between two interval scale variables. Now, an obvious relationship should be between the height and weight of students. So what I'm going to do is get rid of all the columns, except for those two, including the respondent column here. Like so. And then, of course, it's important that for each respondent that they have both a height and a weight. And so what we should do is just do a quick sort here of each column and see if there's any blanks. They'll pop down to the bottom here. And so notice that I've highlighted a particular row here, and that's just to make sure that when we do a sort that they all stay together, because we have a height and a weight for each respondent. So let's click anywhere in the height column here, and I'm going to go to data and then A to Z, and then I can go down to the very bottom here, and it looks like actually there's no problems in terms of heights here. I'll get rid of this blue line here. Now let's do the same with weight, so I can click anywhere in the weight column and go down to the A to Z, and oh, there is one person here who actually didn't put in their weight here. So I'm going to get rid of that. Now what I'm left with then is every respondent here has a height and a weight specified here. I can leave it actually in this form here, or I can go and sort back according to the respondent. It really doesn't matter, but it's probably a good idea just to check to see if these guys stayed together, and they did. So this is good. Now, when we're talking about figuring out the correlation between two variables here, it doesn't matter which order we have them in, which is the X and which is the Y. But because we're going to be talking about simple linear regression as well, just as more of an aside on this one, it is important to recognize which is your X variable and which is your Y variable, because your Y variable is your dependent variable and your X is your independent variable. And we're asking the question about how much does the X variable explain the Y. Now remember that in stats, it's difficult to prove causation when you're dealing with socioeconomic problems and so on. But let's take a look at height and weight here and just ask the question that if there is a relationship and if there is a causality between them, then is it the height of the person that determines the weight of the person, or is it the weight of the person that determines the height of the person? Well, it's probably that the height of the person determines their weight, right? The taller that a person gets, the more likely it is that they weigh more. And certainly you can think of that in terms of kids growing up into adults. And yet, in terms of weight determining height, you can certainly, for adults, you can have very slim people, or you can have people with more weight on them. So we would to say here that the y variable is the weight and the x variable then is the height. Now, incidentally, if I was using the simple linear, or using, pardon me, the regression tool, which is built into the data analysis tool pack here, I would need to have the y variable on the leftmost side. So in other words, I'd need to switch the position of the heights and the weights. In the template that I'm showing you, I actually have the x first and then the y. So they're actually in the correct order here, where height is the x variable, and it explains, or we're asking the question, does it explain the weight, which is the y? So for this template, it'll be the x and then the y. Of course, we're not going to need the respondent column now. That was just used to make sure that we sorted out any blanks and so on. So what we're going to do now is we're going to highlight the height and the weight and go all the way down to the very bottom here. I'm going to copy those, and then I'm going to open up a file here called the Correlation and SLR template, and you can find that in the supplementary files folder. This is pretty simple to use. All you need to do is to go down here where it says the X and the Y, and in the orange cell here, because I've highlighted the titles, I'm going to click in the orange cell here on the upper left here, and right click, do a paste special, and put in values. The other thing that I can do up here is I can change my hypotheses. The hypotheses for a correlation is that rho is equal to 0. The default is two-sided, that it's not equal to 0, but I can change this to either a one-sided or a two-sided hypothesis. So in our particular case, we might say, well, if there's a relationship, we would expect that there would be a positive relationship, that the taller the person, the more they weigh, and vice versa. So let's do that. Let's change that way. All right, let's take a look at what we've got down here. It's really important that you need to go and check normality. So I'm going to click over here on normality and check to see if the Anderson-Darling test for normality holds. Now, the null hypothesis is that the variable is normally distributed, and there's a separate test for the x and a separate test for the y. So there's two normality tests. Now, this seems to be a problem here in that in this particular case for weight, it says that we reject HO, which would mean that they're not normal. However, we don't have to worry about that when the n's are large enough. Now, of course, in a correlation test here, we have got the n's are going to be exactly the same because they're matched, right? Each respondent has a height and a weight. So if the n is at least 30, the central limit theorem kicks in and we don't have to worry about what it says down here. So this is really only applicable if the n is less than 30 and you end up rejecting either one of these. So in this particular case, let's say n was less than 30, we're fine with height, but we would have a problem with weight. And that means that we really can't trust the results here. We need to not use the Pearson test, but the Spearman's test. So the Pearson's test is used when you're dealing with interval scale variables, interval versus interval, and that normality holds. Or in our case, because the n was large enough, the central limit theorem kicks in, and so we don't have to worry about normality. So we can use our results here. Otherwise, if normality fails, then we would use this guy here. While we're in the area here, what I like to do here is just show you that, and I'm going to need to just make this a little smaller here, like that. I'd like you to take a look here then at the results that we've got here. We end up rejecting HO, and with a p-value of 0, it turns out actually that we'll end up with regression analysis here, we'll end up with the same p-value. Now, this maybe isn't the best example of this because it rounds to 0, but the p-value for the Pearson's correlation test will be exactly the same as the p-value for the x variable, which is height, in a simple linear regression. And so that is interesting there. The other thing here is that if we take this r and square it, so 0.592 squared, we'll actually get our r squared value there. Just going to make that a little bit bigger so you can see that. So that's also interesting as well. And then the other thing too is that the t star value for the simple linear regression turns out to be the same as the t star here for the Pearson. So we're really talking basically the same animal here, but the nice thing about the regression output is not only does it show you that there is a significant positive correlation, right? We reject HO, low p-value, okay, high t star value, and it's positive, and that corresponds, of course, to the positive r value here. And so not only do we have a positive relationship here, but we can describe the relationship over here with the regression output. And so this is saying here then, we have a negative intercept, which is not really a problem here because what that would seem to indicate is that somebody of a height of 0 weighs minus 81 pounds. But that's not really a problem. It's just the extension of the regression line down to where height is equal to 0. Practically, height is within a certain range here. I think we're talking about, I think the lowest was something like 140 or something centimeters. So when you have positive heights of 140 centimeters or more, then you'll end up with positive weights. That's all it's saying here. But what it is saying then is that on average here, what we have is that for every increase in centimeter, then the weight is going up by almost a kilogram. That's the weight there. So that's how we would tend to use that. Then we've got confidence intervals here for the intercept, and for, more importantly here, for the x variable, the height. We also have down here the most extreme residual, so we'll talk about that more in Unit S. But when you have a residual here which is outside of the plus or minus 2 range, it means it's an outlier, and that can be pulling the regression line in some sort of way here and affecting the results. So we might want to get rid of those extreme results there and just go and find out where those are. That particular one there is, we could probably find that quite easily here. Where's the extreme residual here? Right there. So it actually has a line right there that tells you where the most extreme residual is. And then we could, if we wanted to, we could get rid of those values there. Now we'd have to move these guys up like that. And now we'd have 80 observations here. We still have an extreme residual here, and so we could go through that process several times, but what you will see is that the r squared will actually start to get larger and larger as we go, and the r will change. It should actually also get larger and larger. Before it was about 0.556, I think it was 0.59, and now it is a lot more. It's actually 0.65. So that's the first problem that I want to show you here. Let's get rid of these data now, because I want to show you how you handle the problem when we're dealing with where one of the variables or both of the variables are ordinal in nature. So let's go back here And we've taken a look at height and weight, found the relationship between them. Let's take a look at two ordinal variables. So these are TV and movie ratings. So let's get rid of all of the values here. It's set for the TV and movie ratings, like so. These are ratings on a 10-point scale where 1 is terrible and 10 is awesome. We're going to do some sorting here just to make sure that there are TV ratings all the way down here. And we'll do the same then for the movie ratings. We'll sort that column as well. And we're good, actually. And I think let's go back up here where we were. And yeah, these guys stayed together, so that is good. Now what's important to note about these is that they're both ordinal in nature. So I'm going to copy them. Doesn't matter which one I have first. Doesn't matter which is the X or the Y in this particular case here, because we're not looking at this as a regression. But I'm going to come back to the same spot here, clear out what I had before, right click, and paste the values. Now, of course, I can go up here and say, I want to test to see the relationship between these two. If I have hypothesized that somebody who rates their TV ratings high probably also rates their movie ratings high, then I would change this as a greater than as the HA here, that we are hypothesizing that there's a positive relationship here. The default is always that there's either a relationship or there's not a relationship. So the alternative is that P is equal to, or rho is equal to 0. We can also change our alpha here. But the important thing I want you to note here is that we only look at the Spearman's results here. And the reason is that they're two ordinal variables. And so we don't have to worry about normality down here. Now, normality, if these were interval, it's not a problem anyways because n is at least 30. But we don't even look at this page because we're dealing with ordinal variables. And so we're not asking the question whether they're normally distributed. We also don't look here at the regression because that's only when you're dealing with interval versus interval. So the only thing that we look at here is these Spearman results there. And so we can take that, the part that I've got highlighted there, copy and paste them, and we can see that there is a relationship between these two. Actually, in this particular case, we could probably just take that table right there because we know what the variables are. And this says that we reject HO due to a p-value, which is quite low, and our correlation value, our Spearman's correlation, is 0.448. It is a positive correlation, so there is a positive relationship between the ratings that people give movies and the ratings that they give TV. So that is that particular problem. Let's do one more quick one here. I'm going to get rid of the data here. And I've gone back here. I've changed this to not equals to. And I'm going to do sleep versus TV. Now, TV ratings are ordinal in nature. They're ratings. And then sleep is the number of hours of sleep. So let's get rid of those guys. And that is interval in nature. So what I've got in this particular case then is an ordinal variable and an interval variable. The important thing to note is that if either of them are ordinal, all you use is the Spearman's test. So let's just really quickly do this one. I'm going to sort according to TV. I think we've done that before and found out that there is no blanks here. But you can see that there are some blanks here for the sleep. So we're going to sort according to those guys and then just get rid of these rows right here. So that leaves us with fewer people here. But now everybody has a TV rating, and they've put down the number of hours that they sleep. So I can go up here and I can highlight these two columns. Yeah, those guys stayed together, so everything's sorted well together. Copy that, move over here. Doesn't matter which order that we have them in because we're not looking at the regression output. We just do a paste special, values. And again, we don't worry about normality. We don't look at the Pearson's correlation. We don't look at the regression output. This is all we look at. It's important, of course, to determine what your alternative hypothesis is. The default is that they're just simply related, or sorry, not related. No, let's try that again. HO rho is equal to 0 means that there's no correlation between them. And then this is that there is a significant correlation between them. And depending on your hypothesis, you could be hypothesizing that it's either a positive or a negative one. In our particular case here, we end up actually not rejecting HO. And so there's no significant correlation between the how you rate movies, TVs, shows, and the amount of sleep that you get. I thought maybe that people who really rated them high might actually get less sleep because they're spending more time watching TV, but this seems to indicate that there's very little relationship here. No significant relationship. It's got a very low R value of 0.0103. So I would copy and paste that over, and that's how you use this particular template to do correlations. Remember, we looked at interval versus interval, and that's where you need to look at normality. And if that passes, then you can use the Pearson's correlation, and you can use the regression here. But if either of the variables are ordinal, then you don't worry about normality or Pearson's or regression. You just use the Spearman's correlation. So that's where I want to end this lesson here. Thanks for watching.